Hey everyone, in this presentation I will be discussing the chemistry of plastic recycling. Before getting into the true heart of this subject, however, I feel a brief discussion of the topic as a whole is necessary. So, what is plastic recycling? Plastic recycling deals with how we manage our existing waste and also constitutes a component of circular economies and zero waste systems. Although problems started arising with plastic waste in the 1960s, there's been a ton of pushback until recently regarding the need for high-efficiency recycling. As more and more people have started to look into recycling plastic materials, however, it has become apparent that there is a lack of knowledge on how to do so effectively. Plastic has been around for about a century and has become a huge part of our lives, but in just 70 years, over 8.3 billion metric tons of plastic have been produced, with more than 6.3 billion tons becoming waste and only 9% of this being recycled. Various issues with contamination, such as mixing non-recyclable and recyclable plastics, or recycling plastics soiled with adhesives, chemicals, food, and remnants, contribute greatly to this discrepancy. Additionally, the different makeups of different types of plastic cannot be mixed in certain instances and thus cannot be separated and recycled effectively. This leads me into the first main relation between our lessons and this topic. Plastics are made up of different types of polymers. The type of material being recycled plays a huge role in whether or not it can be used again, and this all comes down to the most basic units of the substance. The 7 main plastics are PETE or PET, HDPE, PVC, LDPE, PP, and PS. There's also an other category. PETE is polyethylene terephthalate, one of the most common types of plastic. It is a resin used for the manufacture of food containers and plastic bottles and is widely recycled. The polymer PET is comprised of smaller units of ethylene terephthalate in a long chain. HDPE is high-density polyethylene, which is more rigid than PET and is used in sturdier products like detergent bottles, food and drink storage, bottle caps, thick shopping bags, and non-single-use products like toys, helmets, and piping. It is also widely recycled, but is not as common. PVC stands for polyvinyl chloride, one of the most versatile, and is used for water and waste pipes, flooring, signage, and even for furniture. However, it is rarely found in general plastic recycling collection as it is toxic when processed. PVC is comprised of smaller units that are chained together in this polymerization reaction. LDPE stands for low-density polyethylene, which is not as strong as HDPE, but is highly resilient and is used in large ranges of products such as containers, playground fixtures, and trash bags. It is recyclable, but mostly excluded because these types of products pose a risk of clogging the machinery. PP stands for polypropylene, and this is used in injection molding, bottle caps, surgical tools, and in clothing. It is recyclable, but is also often rejected. It is made up of a string of propylene molecules that are combined in the following reaction. PS is polystyrene and is frequently used in disposable plastic containers for food, insulated containers, and in packing materials. PS is abundant but rarely recycled because it is not cost-effective and is more commonly known as styrofoam. This is made up of smaller styrene units polymerized into a longer chain. The other category covers all other mixtures and types of plastic which are usually not recycled in general collections. Currently, there are 2 types of recycling that exist: mechanical and chemical recycling. Though chemical recycling is more effective, it is much less common as it is extremely expensive. Most recycling is done through the mechanical process, which is done in the following steps. The first step is collection and distribution. In this step, the materials are collected from homes, businesses, and other establishments by the local government or private companies. The second step is sorting and categorizing, which is the sorting of the plastics into their different types. They are also sorted by color, thickness, and use in this step. Machines at the recycling plant do this to limit any type of contamination. The third step is washing, and is a very crucial step as it removes impurities which can later impede the operation or ruin an entire batch of recyclable plastic. Impurities targeted in this step are labels, adhesives, dirt, and food residue. The next step in mechanical recycling is shredding, and in this step, the plastic is fed into shredders that break it into much smaller pieces. The resized pieces can be used for other applications without further processing, such as being added to asphalt or even sold simply as raw material. This stage also allows many remaining impurities, such as metals, to be collected with a large, strong magnet. The fifth step in mechanical recycling is identification and separation of plastics. In this step, plastic pieces are tested for their class and quality and are segregated by density. Then after this, there is a test for air classification to determine the thickness of the pieces. The final step in mechanical recycling is extruding and compounding. In this step, the particles of shredded plastic are transformed back into usable product for manufacturing. The shredded plastics are melted and crushed together to form pellets. While this all seems to work fairly well, there are several problems with mechanical recycling. One of these main problems is that mechanical recycling most often leads to downcycling. Basically what this means is a soda bottle will never be a soda bottle again. So, what do we do about this? Well, this brings up the second kind of recycling, chemical recycling. Chemical recycling could be a way around some of mechanical recycling's shortcomings, as its processes are more tolerant of contamination, can yield polymers that are identical to their originals, and can potentially eliminate downcycling. Chemical recycling also closely relates to our lessons on polymers and polymerization. Chemical recycling promises to make pure new plastic an infinite number of times, as it involves taking plastics apart on the molecular level. The molecules that make up plastics, the polymers I discussed a few minutes ago, are made of smaller monomers, the subunits I also discussed. The recyclable plastic is chopped up and treated with some combination of water, heat, pressure, and enzymes or catalysts, which make it possible to disassemble the polymers back into their monomers and then to separate the building blocks from dyes and other contaminants. Then, the monomers can be pieced back together into a good as new plastic. This process is the opposite of polymerization and is called depolymerization. PET has so far proved to be the easiest to take apart. Carbios, a French company, is testing enzymes produced by microorganisms to break down PET. Another type of chemical recycling occurs in pyrolysis plants. Pyrolysis is the process by which long polymer chains are cracked into short-chain hydrocarbons like diesel and naphtha under low oxygen conditions and temperatures of more than 400 degrees Celsius. Pyrolysis is best suited to handle a mixture of polyethylene and polypropylene. While pyrolysis today is focused mostly on fuels, chemical companies hope that more firms will use the process to make naphtha, which can be fed into petrochemical plants to become polyethylene and polypropylene once again. So, after learning all of this new information, you're probably asking, why is this relevant? Well, it turns out that plastic recycling actually has implications in numerous industries and plays an even larger role in our society than you might think. The most obvious and immediate relevancy of plastic recycling is probably to get rid of the excess waste on the planet. As many know, landfills are being filled at exponential rates, and it's only a matter of time before we run out of places for our waste. Increasing efficiency of recycling will be extremely important if we want to keep control of our waste management systems. Beyond the environmental concerns, recycling also plays a huge role in our economy. To begin, recycling systems create jobs. Recycling also allows businesses and corporations to avoid the costs of disposal and reduce the need to use solid waste services. These benefits are just a few of the many ways plastic recycling is relevant to our lives. Plastic recycling may seem like an unsolved puzzle at this point as we scramble to find a more efficient system, but amidst all of these complicated processes, chemistry seems to be telling us that we may find a solution if we go back to the basics.